is also on the handouts I give you today, and this handout simply is a duplication of the introductions in the homework. So I just try to go over that one. And transfer function is a concept borrowed from control, and which we're going to have this class offer in the spring. But in some way, I think our textbook introduced this concept in a pretty much messy way. I don't like it. And actually that's confusing. So here I will come up with my own approach and to introduce this topic. Transfer functions is a very powerful tool. And before we go over the technical details, and I can give you one essential part why we use transfer functions. The transfer function is so powerful is in its capability of, listen this carefully, transferring differential equations into the algebraic equations. So that means, sometimes when we solve for the differential equations, because that's a derivative or involving integration, it's a little bit time consuming. If we're working on the algebraic, that is always easier. Okay, so basic transfer functions is play a role, a way to transfer all the information that suppose, for example, equation of motion is in differential equation form. We are able to transfer that one into the algebraic. And how to do it, and just keep this in mind. So basically, most of your work with the transfer function is doing some kind of algebraic summations, subtractions, multiplications, divisions. Okay, that's it. So the outline for here, I right away to jump into these sections, but we'll go back to cover something. The transfer function is so powerful because on the mathematical side, it gives us a little bit easier process to reduce our rigor to handle dynamic systems. Okay, that's a mathematical side. On the other side, transfer function allow us to solve for dynamic systems, to solve for this steady state response to many kinds of the force excitations. And right now, what I say so is this. Right now, we have individually looked at the system response to either sine or either cosine. But since we have no systematic way to look up the system response due to the combined, okay? Not to mention the system response, which is non-harmonic. So we might have other system response, say impulse. Impulse just like this, I knock it, and that gives the stable impulse. Or we get the step input. The step input is this. I just stick there, and right now it's a constant loading to this table, right? Okay. Or even say the constant ramp input. That means I pull in this one. So right now this is a constant. Okay, the constant ramp. And including any other things. Okay, so the transfer function will allow us to do this kind of to solve for this steady state response to many kind of the regular common forms. And if we still use the traditional approach, directly solving differential equations, I can tell you many times we would have a hard time to deal with such non-harmonic force form. Okay, so basically, I would say the transfer function will be additional mathematical tool, and I think that's worthy of our time to spend on this one. And in chapter 3, the direct outcome of learning the transfer function is this. We want to know the system response, and that is due to the combination of sine and cosine together. Okay, so we know that if we already know if we want to combine the sine and cosine, one way is to express in terms of the complex functions. Okay, that is one of many other ways we combine the sine and cosine together. Not the unique one. Okay, basically we combine it into this is called the complex function. Complex function by definition, that is a cosine plus I sine. Okay, somehow this appear with some kind of complex in the imaginary part, but later on we can deal with that one. Okay, but here I can tell you this is one of the approach. The other approach is using the Fourier series transformations. Okay, then that one we're going to talk about in next chapters. So again, we're back to our learning the transfer functions. The one direct outcome is that will allow us to solve for the steady state response of this form. Okay, so that one, again, that will overcome many tedious, bothersome calculation steps using our old approach. Let me define our old approach as the approach what we have learned so far. Okay, so that's the one. And then additional outcomes of learning transfer function is we try to get ourselves ready for chapter 4. So in chapter 4, I think we're going to still using the concept of transfer function to deal with the response of the system to this kind of force. Let me summarize here. So, for example, this is our systems, and okay. So right now in chapter 3, and this is the type of the force, and one is harmonic excitations. So that means F now cosine omega t. Okay, and this one also can be said cosine omega t and plus F now sine omega t, something like this one. That one is we're going to study now. And in chapter 4, we're going to have the response is this time. Okay. Say we have an impulse. Impulse at any time, say t0, and t0 can be arbitrary, can be initially at 0, or t0 can be any time, say 1 second, 2 seconds, whatever. Okay, and we might have the force that is a constant. Say this is 1 or 2 or 3. This is called the step input. Step input, that means the loading is constant there. Okay, and we might have they call the ramp. The ramp input is with arbitrary slope beta. Okay, and furthermore, we might have arbitrary. And I don't think our learning techniques solving the non-homogeneous solutions of the differential equations will be allow us easily to deal with this kind of the non-homogeneous term. Okay, and that is the contents of chapter 4. So I would say chapter 4 will be very, I would say, mathematically rigorous. In certain portions, it will be challenging. Okay, just kind of give you a head up. But that's a way we have to deal with. Okay, but trust me, I will give you enough. That's my duty. I will give you enough preparations and to deal with this kind of things. Okay. So that is the second outcome. We're going to learn transfer functions, and so here in these chapters, in particular, we're going to deal with this one. So this is part of the. Are you okay?
Yeah, I'm good.
This is the part of the sections here we're going to deal with. So before we're doing this one, then we want to introduce and what is the concept of the transfer functions. Okay, with transfer function ready, and again, transfer function is to convert this is the mx double dot plus cx dot plus kx equal to ft. Okay? And why not? Let me switch my symbols, but that won't affect. So let me use all the lowercase to indicate information in the time domain. Okay? So let me switch my symbols here. So the transfer functions basically is to teach us how to convert the information in the time domain. This is the time derivative in dynamics into the algebraic informations. Okay. And before we move on, then let me tell you right away the very quickest form. And with that form ready, you can get at least 50% of the information for the transfer functions. And listen here carefully. To obtain this is the dynamic form. So the corresponding algebraic form of the dynamic system is this. And listen carefully, and right now I only said once. Okay, and then when I said, don't ask me why, because I directly give the result. Later I'm going to explain why. Okay. So for this one, you simply replace the double derivative term with s squared and keep the coefficient the same. And replace the first derivative with s and keep the coefficient the same and keep the operation the same. And for k, that is nothing. So for x has no derivative, so simply you can say that is a 0. So basically that is 1. Okay. So that is the term. And then how to deal with the x? And after x, you simply replace x with the parameter called the function of s. And the corresponding term for f, that has a corresponding term in f. This is called the time domain. That means all the parameters are governed in the time. This one is in algebraic form. We call it in the S domain. S domain. Okay. So basically, from here you can see simply x double dot convert into algebraic form is this s squared times x. So this is in the time domain. Okay, and in the x derivative, you simply do it is s times x of s. Okay, and then if x of t, you simply convert it is capital of s. So basically, this is the expressions of the dynamic term in the time domain. This is the transformed, the counterpart in the s domain, just like this. So with the introduction of these particular s parameters, we will be able to convert the time dynamic information into the algebraic. And that's the key. This is the simplest form of the process to get the transfer functions. And this one, keep this in mind, that will be sufficient for dealing with all the problems in vibrations. Okay? And so that is this one. And then keep this in mind, and then basically you have obtained the half of the necessary information for the transfer functions. So right now we show how to do the transfer functions here. I'm not very good in following this slide I have, but I will try. For this one, we've been introducing here, actually this is called the Laplace transform. I'm not come up with this one on my own arbitrarily. No, this is not magic. Basically, this is a result of the taking the Laplace transform. If you remember the Laplace transform, have you been exposing to this topic before? Yes, right? In which class? DDQ. How many weeks in this topic? 2 weeks? About 1 to 2 weeks? So that is not much. Yeah. But I think that is good enough. If you remember the Laplace transform, we're using the notation. Okay? So for this one, let me use the official notations. Basically, the x dot of t. We convert it into the counterpart, that is here. Let me define the x of t is Laplace transform term. Let me define as a capital of S. Okay, and this one basically is coming from the definition of the Laplace transform. The Laplace transform is this: capital of S is equal to, if you remember, that one is e minus st of xt and dt, and t is from this is sometimes this is indefinite integral, or sometimes people say from minus infinity to infinity, and integration is take on t. So basically the whole thing come up with is a function of s. S is the parameters we use in Laplace transform. These are fundamental definitions. So for this one, basically this function, if you want to calculate this one, you simply take these patterns. You simply replace this one as x dot here, then you can obtain the corresponding. You just simply plug into the definition here and do the calculation. But here we have a table, right? If you remember, we have a Laplace transform tables. So many tables of so many functions. So here one example is this. So this one, we know that this will be equal to s times capital of S. Okay, so s multiplied with this one and minus initial conditions. For example, the Laplace transform of the double derivative will be equal to s squared times this minus s times x dot and minus x0. Okay, this means the initial conditions, initial position, initial velocity, initial positions. Okay, and so this is the fundamental complete description of the Laplace transform for the dynamic information for its first derivative, for its second derivative. And with these things in mind, apply it to our dynamic systems. Our dynamic systems is looking for steady state response. For the study of the steady state response, so here I want to emphasize, I gradually kind of kick into the exact information in such a way we are not playing with the math arbitrarily. Okay, we do this carefully. So we want to study the steady state response. Again, for this example, back to our problem here, we want to know the steady state response of the system to such force, right? If you remember from the beginning, we're interested in the steady state response. So when we want to know the steady state response, and the way is that we don't need to consider the contribution from the initial conditions. So you know the steady state response, the total response have two portions. One is the transient response, one is the steady state response, right? The steady state response is the system response to harmonic, to the force, not to the initial conditions. So when we consider steady response, we can take all the ICs equal to 0. Because the steady state response simply doesn't consider the contribution from the initial conditions. So once we take this, consider steady state response, then we take the initial conditions to 0. Under that thinking, then the two terms can be knocked out. So that's the reason why when we take the Laplace transform without the initial conditions, and that is the way we do it in preparation for the transfer functions. Okay, pretty good? So two pieces of information. The first one is you memorize this kind of the rule. The second one, the rule will be valid when initial conditions is not included. Good? Any questions? No? Okay, now we come to the definition of the transfer functions. Transfer function is defined by this. So now before I define this, let us consider this. So you see the system is respond to any force excitations. So the respond to the force, I would say respond to any input. So here I want to convert your thinking into the more controlled way. We treat the force as the input, and we treat our response, that means the degree of freedom xt. So this is our response to the input, so this is the output. So simply we introduce additional term that is more relevant to the control, okay? Because the transfer function is originated from the control theory. So in this way, the transfer function is defined by the relation between output and input. That's it. This is a fundamental concept of the transfer function. Transfer function simply is to transfer the information, basically the ratio between the output and input. And for our output, basically this one is described in the S domain. Okay, I want to emphasize in the S domain, so not to put this one. Okay. In the S domain. Okay, so keep this in mind. We can further to play with. What is our output? Output is X. We express X in the S domain. And what is our input? Input is f of t, and that expressed in the S domain, that is f of s. Good? Good? What is this? You see, this is the term multiplied with x equal to this. So x over s, would that be equal to 1ms squared plus cs plus k? Good? So simply transfer function for this particular system is this one. But in general, its definition is simply found here. So for all kinds of the system, dynamic system, as long as you can play with, you can plug in this table, convert from its own given dynamic equation of motion into this algebraic form, you can right away to write out the transfer functions. So today we stop here, and then coming up Wednesday, we're going to start from here to see how can we utilize this function to do something for our vibration. Okay, thank you.